Welcome back to the deep dive. Today, we are stepping into a world that, on the surface, seems incredibly routine. You walk into a high school gym or a community center, you smell the antiseptic, you see the cots, and you see people squeezing stress balls. It feels almost, passive.
It does feel passive. It's a community service, right? You give a pint, you get a cookie, and then you just go about your day.
Exactly. But today, we're going to completely dismantle that image. Because once that bag leaves your arm, it enters a world that is equal parts industrial manufacturing and high-stakes biological detective work. We're not just talking about topping off a fluid level in a car engine here.
Not at all.
No.
If you take nothing else away from this deep dive, I want you to shift your perspective on what that bag actually is. It is not just a fluid. It is a pharmaceutical product. It is a manufactured drug with a strict shelf life, chemical preservatives, and, intense quality control. And more than that, it is a living transplant.
A living transplant. That is the hook. We are taking living tissue cells that breathe, that metabolize and age from one human being and integrating them into another. And the source material we have for today is, well, it's pretty much the Bible of how that happens. We are looking at the ABB standards, the strict donor protocols, and the intense chemistry of immunohematology.
It is a massive topic. Our mission here is to really decode the complexity behind the scenes. We are going to trace the journey from the strict criteria of the donor, who actually gets to give and why, to the biochemical magic required to keep those cells alive in a plastic bag. And finally, the detective work required to ensure a patient's immune system doesn't treat that life-saving gift as, well, a deadly invader.
And when we say detective work, we mean it literally. Imagine a hospital lab at 2 a.m. It's not just microscopes and test tubes. It is a highly controlled environment where one wrong move, one clerical error, or, one missed reaction in a gel column can be fatal. It is a matching game involving genetics, immunology, and invisible antibodies.
Oh, it's a very high-pressure environment. You're dealing with strict expiration dates, temperature controls that have to be monitored to the 10th of a degree, and genetic codes that have to align perfectly.
So let's start at the very beginning, the gatekeepers. Before a drop of blood is even collected, there is this gauntlet of selection criteria. I was looking at the whole blood standard in our notes, and frankly, I was surprised by how specific the math is.
It has to be specific because the primary goal is twofold. Safety for the donor and safety for the recipient. We have to ensure the donor can physically handle the loss, and we have to ensure the product is potent enough to actually help the patient.
Right. So physically, you have to be at least 16 years old, depending on state law. And you can't be running hot. The temperature cutoff is 37.5 degrees Celsius or 99.5 Fahrenheit.
That is the first line of defense. If you are feverish, you are deferred. It could indicate an active infection, bacterial or viral, that you definitely do not want to pass on. But it also protects the donor. If your body is already fighting something, losing 500 milliliters of blood is going to stress your system significantly.
Then there's the iron check, the famous finger prick.
The hemoglobin and hematocrit levels.
Yeah.
For an allogeneic donation, that means donating for someone else, not yourself, your hemoglobin needs to be at least 12.5 grams per deciliter.
12.5.
Or if they measure hematocrit, it needs to be 38%.
If you are below that, you are anemic. Taking a pint of blood out of you isn't safe. But here's the detail I found really interesting in the source material. It's not just fill the bag until it looks full. There is a very specific calculation for how much blood they can actually take based on your weight.
It's precise. The standard is 10.5 milliliters of blood per kilogram of donor weight.
10.5 ml per kilogram? Why that specific number? Why not just take a standard amount from everyone who walks in?
Well, there are two reasons. First, physiology. The 10.5 ml per kilogram ensures that the donor doesn't lose a dangerous volume of blood relative to their total mass. If you take too much from a smaller person, you risk hypovolemic reactions, fainting, seizing, or worse. But the second reason is actually about the chemistry inside the bag itself.
The bag isn't empty when you start, right?
Correct. Standard collection bags come pre-filled with a liquid anticoagulant preservative. It's usually about 63 milliliters of fluid designed to mix with exactly 450 or 500 milliliters of blood.
So it's a recipe.
Exactly. It's a chemical ratio. If you have a donor who is underweight, or if the flow stops early, say the vein collapses, and you only collect, say, 350 milliliters, you have a problem. It's called a low-volume unit.
Because now you have too much chemical and not enough blood.
Precisely. The ratio of citrate, that's the chemical that stops clotting, is way too high relative to the plasma. If you transfuse that plasma into a patient, it could be toxic. It could mess with their own electrolytes.
So if you don't fill the bag, the plasma is trash.
The plasma is discarded, yes. The red blood cells might still be salvageable if you label them correctly, but the plasma cannot be used for transfusion. So the physics of the collection bag dictate the eligibility of the donor.
That is fascinating. It's not just about the person, it's about the container. Now, let's talk about the no list, the deferrals. This is where it gets into the art of risk management. And reading through this, it's clear that deferrals are really just a timeline of risk.
Deferrals are all about incubation periods. We are asking, if this person was exposed to a pathogen, how long until we can be sure they don't have it? Or how long until their body recovers?
Let's break down the timeline, starting with the short term. 2 days. Who gets put in the penalty box for just 2 days?
Aspirin users. But there's a huge nuance here that often confuses people. You can take aspirin and donate whole blood. That is fine. This 2-day deferral specifically applies if you are donating platelets.
Why the distinction? Why does aspirin ruin platelets but not red cells?
Well, this is where we get into the cellular mechanism. Aspirin is an acetylsalicylic acid. It permanently acetylates an enzyme called cyclooxygenase inside the platelet.
Cyclooxygenase, that sounds important.
It is vital. That enzyme is what allows the platelet to become sticky and form a clot. When aspirin hits it, it breaks that enzyme forever. Now here's the kicker. Platelets are fragments of cells. They have no nucleus. They have no DNA machinery to build new proteins.
So they can't repair themselves.
They cannot. Once a platelet is aspirinized, it is broken for the rest of its life, which is about 7 to 10 days. If you are donating a unit of platelets and you took aspirin yesterday, you're essentially donating a bag of broken machinery. It won't help the patient clot.
That makes total sense. If I'm a patient bleeding out, I don't want broken platelets. But for whole blood, it's diluted enough that it doesn't matter.
Exactly. In whole blood, you have a mix of fresh and old platelets, and the volume is small enough that the patient's own platelets can compensate. But for a dedicated platelet transfusion, it's an absolute deal breaker.
Okay, moving up the timeline. 2 weeks. This seemed to be mostly about live vaccines.
Correct. If you have had a live attenuated vaccine, measles, mumps, polio, yellow fever, you wait 2 weeks. The virus in the vaccine is alive. It has been weakened, sure, but is biologically active.
So theoretically, it could replicate.
Theoretically, it replicates in your body to give you immunity. During that window, there is a tiny non-zero chance that the virus could be present in your bloodstream. If we take that blood and give it to a leukemia patient with no immune system, we could accidentally give them the measles.
Which would be catastrophic. Okay, 4 weeks for rubella or chickenpox vaccines. Then we hit 6 weeks.
6 weeks is the standard deferral following the conclusion of a pregnancy.
Is that for the baby's safety or the mother's?
Mothers. Pregnancy is a massive physiological drain. It depletes iron stores. It changes fluid volumes. The 6-week wait allows the donor's body to return to baseline so that donating doesn't harm her.
Then we jump to the big one, 12 months. This is a laundry list of high-risk activities. Needle sticks, sexual contact with someone at risk for HIV or hepatitis, incarceration.
This is the window for slow incubating viruses. HIV, hepatitis B and C. Even with our modern testing, which is incredibly good, there is a window period where a person can be infected but test negative. The 12-month deferral acts as a massive buffer zone to ensure we aren't in that window.
And incarceration is on that list, specifically if it's for more than 72 consecutive hours.
Yes. Correctional facilities are statistically associated with higher rates of infectious disease, transmission of tuberculosis, hepatitis, HIV. The 72-hour mark is the cutoff where the risk is deemed significant enough to warrant a 1-year wait.
Travel is another big one for the 12-month list, specifically malaria endemic areas.
Right. If you travel to a place like Nigeria or parts of Brazil, you wait a year. This ensures you haven't picked up the malaria parasite. But notice the distinction. If you actually had malaria or if you lived in an endemic area for a long time, say more than 5 years, the wait is 3 years.
3 years? Why so much longer?
Because malaria is sneaky. The parasite, Plasmodium, can hide in the liver. It can go dormant for a long time and then reemerge. A simple blood test might miss it if it's hiding in the liver. So we wait 3 years to be absolutely sure the donor is clear.
It's persistent. Wow. Now we have to talk about the permanent deferrals, the ban for life list.
These are conditions where the risk is just too high or the pathogen is undetectable. Parenteral drug use, IV drug use, is a permanent deferral due to the extremely high risk of blood-borne pathogens.
And family history of CJD.
Creutzfeldt-Jakob disease. This is the human equivalent of mad cow disease. It is caused by a prion, a misfolded protein.
The prions are terrifying because they aren't even alive, right? You can't kill them with antibiotics or anything.
You can't kill them, and we cannot easily test for them in a blood donor screening. And the disease is 100% fatal. If your family has a history of it, implying a genetic susceptibility or exposure, we just cannot take the risk.
Also, anyone who had viral hepatitis after their 11th birthday is permanently deferred. Why the 11th birthday? That seems like such an arbitrary line in the sand.
It sounds arbitrary, but it's based on statistical likelihood. If you had hepatitis as a toddler, it was likely hepatitis A, which is foodborne and doesn't result in a chronic carrier state.
Well,
But if you get hepatitis after age 11, the likelihood shifts. It is much more likely to be hepatitis B or C, which are bloodborne and can stay in the system for life.
so age 11 is the proxy for adult-type exposure.
Got it. So let's say you pass all this. You are healthy, you haven't traveled to a swamp recently, and you are ready to donate. The collection process itself involves scrubbing the arm with iodine. That's for bacteria, right?
Yes, we use an aseptic method, usually a two-step scrub. You are sticking a 16-gauge needle, which is a large bore needle, into a vein. If you don't clean that skin perfectly, you are punching a plug of skin bacteria directly into the bag.
And blood is warm and nutritious. It's perfect food for bacteria. Oh, absolutely. Especially if we are making platelets, which are stored at room temperature. If any skin bacteria get in there, they will multiply rapidly. Septic transfusion reactions are a major cause of fatality, so that arm scrub is absolutely critical.
Now, here's a detail I loved, the timer. The collection usually takes less than 10 minutes, but there's a rule. If it goes over 15 to 20 minutes, the unit cannot be used for platelets or plasma. Why is speed so important?
Because as soon as the needle enters the vein, you have triggered the body's injury response. The clotting cascade begins. If the blood flows slowly, just trickling into the bag over 20 minutes, microclots start to form in the tubing.
The platelets get used up.
Exactly. The platelets sacrifice themselves trying to plug the injury in the needle. By the time that bag is full, the coagulation factors are depleted and the platelets are aggregated. The red cells might be okay to use, but the plasma and platelets are, for all intents and purposes, useless.
So a slow bleeder is a bad donor, essentially.
In the context of component manufacturing, yes, that's a good way to put it.
Okay, so the blood is in the bag, the needle is out. Now we enter section 2, the chemistry of storage. This is where the science fiction kicks in. We are trying to trick these cells into thinking they are still in the body, but they are cut off from their life support. They have no lungs to give them oxygen, no kidneys to clean their waste.
That is the fundamental challenge of blood banking. We are fighting a losing battle against entropy. As soon as that blood leaves the body, it starts to die. Our job is to slow that dying process down just enough to get it into a patient.
And we use what the notes call alphabet soup preservatives. Let's decode this. We start with solutions like ACDA, CPD, CP2D. These give you a shelf life of 21 days. What is actually in this stuff?
Well, the main ingredients are dextrose and citrate. Dextrose is just sugar. It provides the fuel. Red blood cells need energy to keep their membranes intact, and they get that energy by metabolizing sugar into ATP.
And the citrate.
Citrate is the anticoagulant. It works by chelating calcium.
Chelating. That's a fancy word. Unpack that for us.
Think of citrate as a chemical sponge. The clotting cascade absolutely requires calcium ions to function. It's a key ingredient in the reaction. Citrate binds to the calcium, effectively locking it up. Without free calcium, the blood cannot clot. It stays liquid.
So sugar for food, citrate to stop clotting. That gets us 21 days. But then we got better. We introduced CPDA1.
The A stands for adenine, and this was a massive game changer in the history of blood banking.
Why is adenine so special?
Adenine is a substrate. It's a building block that helps the red blood cells synthesize ATP more efficiently. It's like giving the cells a better quality fuel additive. It extended the shelf life from 21 days to 35 days.
2 extra weeks. That is massive for inventory management.
Huge. It allowed hospitals to keep stock on hand without throwing it away constantly. But we didn't stop there. Now we have additive solutions, AS1, AS3, AS5.
These are added after the collection.
Yes. We spin the blood, take the plasma off, and then add this nutrient bath back onto the red cells. It contains extra dextrose and adenine. This pushes the expiration date for red blood cells to 42 days.
42 days is the current gold standard. But here's the dark side. Even with all this sugar and adenine, the blood isn't staying fresh, it's degrading. We call it the RBC storage lesion.
Lesion implies injury or degradation.
Yeah.
And that is exactly what is happening. Inside that plastic bag, a biochemical breakdown is occurring.
Let's look at the balance sheet. What goes up and what goes down over those 42 days?
Well, the cells are eating the sugar and producing waste. So lactic acid goes up, the pH goes down, the environment becomes acidic.
Acid blood, not great.
Not great at all.
Yeah.
Simultaneously, the ATP, the energy, is depleting. The cell membranes get weak.
Yeah.
And here's the most critical one. 2,3-DPG decreases.
2,3-DPG. This is the molecule that tells hemoglobin to let go of oxygen, right?
Exactly. It regulates oxygen affinity. I like to think of hemoglobin as a delivery truck. Its job is to pick up oxygen at the lungs and deliver it to the tissues. 2,3-DPG is the key that unlocks the back door of the truck.
So what happens when 2,3-DPG levels drop in stored blood?
The truck loses the key. It picks up the oxygen just fine, but when it gets to the tissues, it can't open the door. It holds onto the oxygen too tightly. We call this a shift to the left on the oxygen dissociation curve.
That is wild. You infuse this old blood into a patient to save them, but the blood refuses to share the oxygen.
For a short time, yes. It creates a paradox where you have increased the hemoglobin count, but you haven't necessarily improved oxygen delivery immediately. The body will regenerate that 2,3-DPG, but it takes about 24 hours.
So fresh blood really is better in that sense. What about what leaks out of the cells?
Potassium. Cells are bags of potassium. As the membranes get old and leaky during storage, potassium spills out into the fluid.
And injecting a high load of potassium is how we execute people on death row, isn't it? It stops the heart.
In massive doses, yes. For an adult receiving 1 unit, it's usually not a problem. But for a neonate, a premature baby with a tiny heart and tiny blood volume, that high potassium in old blood can be fatal. It can cause cardiac arrest. That's why babies usually get fresh blood, less than 7 days old.
All of this storage chemistry assumes the bag stays sealed. We have to talk about open versus closed systems.
Right. A closed system is when everything is connected by sterile tubing. But sometimes you have to open the system, maybe the tubing breaks, or you have to spike the bag to wash it.
Once you break that seal, the clock changes drastically.
Drastically. You have exposed the nutrient-rich blood to air and potential bacteria. If the unit is stored in the fridge at 1 to 6 degrees Celsius, the expiration drops to 24 hours.
From 42 days to 24 hours.
Yes. And if it is at room temperature, it expires in 4 hours.
That is a strict rule. It really emphasizes that bacteria are the ultimate enemy here.
Absolutely, 100%.
Let's move to Section 3, manufacturing components. Because as we touched on, we rarely give whole blood anymore. We chop it up like a car for parts.
Component therapy is the standard. It allows us to treat specific deficiencies. If you need oxygen, we give you red cells. If you need clotting, we give you plasma. It also maximizes the resource. One donation can help 3 or 4 different patients.
And how do we separate them? It's all about the spin, right?
Centrifugation. We spin the blood at high speeds. It separates based on density. Red cells are the heaviest, so they sink to the bottom. Plasma is the lightest, so it floats to the top.
And in the middle.
The Buffy coat. A thin white layer containing the white blood cells and platelets.
Let's look at the products. Red blood cells, or RBCs. We store them cold. What's the expected return on investment for the patient?
The rule of thumb is that 1 unit of RBCs should raise the patient's hemoglobin by 1 gram per deciliter, or their hematocrit by 3%. If I give you a unit and your numbers don't go up, that triggers a whole new investigation. Are you bleeding somewhere else? Is your spleen eating the cells?
Now, sometimes regular fridge storage isn't enough. We have frozen RBCs. This sounded like pure science fiction to me. Minus 65 degrees Celsius.
Or colder, we can keep them for 10 years. But you can't just freeze blood. The ice crystals would shred the cell membranes. It would turn into red soup.
So how do we stop the ice?
We use a cryoprotectant, glycerol. We replace the water inside the cell with 40% glycerol. It acts like antifreeze. It prevents the ice from crystallizing.
But glycerol is toxic, right? You can't infuse antifreeze into a patient.
Correct. When we wake those cells up, when we thaw them out, we have to wash them. We have to rinse out all the glycerol. This process opens the system. So once you thaw a frozen unit, you have 24 hours to use it.
Use it or lose it. Now, you mentioned washed RBCs. Why would we wash blood that hasn't been frozen?
This is usually for patients with severe allergic reactions, specifically people who are IgA deficient. IgA is a protein in normal plasma. Some people lack it, and their immune system sees it as a foreign invader.
So if they get normal blood, even a little bit of plasma,
They can go into anaphylactic shock. Washing the red cells removes almost all the plasma and those IgA proteins. It makes it safe. But the downside is you lose about 10 to 20% of the red cells in the washing process. It's a trade-off.
and then we have irradiated RBCs. We literally zap the blood with radiation. 2,500 centigrade. Why on earth are we nuking the blood?
To kill the T cells, we're worried about a condition called transfusion-associated graft versus host disease, or TA-GVHD.
That sounds horrific. What is it?
Normally, if I give you blood, your immune system might attack the blood. That's rejection. But in GVHD, the blood attacks you. The donor T cells look around, realize they are in a foreign body, and launch an assault on your bone marrow, your skin, your liver.
And this happens if the patient is immunocompromised.
Yes, like a bone marrow transplant patient. Their immune system is too weak to fight back. It also happens if the donor is a blood relative. The genetics are similar enough that the patient's body doesn't recognize the danger immediately, allowing the donor T cells to set up shop and attack. It is almost always fatal. Irradiation prevents the T cells from dividing. It neuters them.
Moving on to platelets. The clotters. These guys seem like the divas of the blood bank.
They are absolute divas.
Yeah.
You cannot put them in the fridge. Cold temperature changes their shape and stops them from working. So they have to be stored at room temperature, 20 to 24 degrees Celsius.
And they can't sit still.
No. They require continuous agitation. They sit on these shaking racks that gently rock back and forth 24/7. If they start moving, the pH changes and they clump up.
And because they are at room temperature, we are back to the bacteria problem.
Exactly. Room temperature is a luxury hotel for bacteria. That is why the shelf life is only 5 days. And by the time you test it and ship it, the hospital usually only has 2 or 3 days to use it. It creates a constant supply chain crisis. You are always running out of platelets.
And there are 2 ways to get them. Whole blood derived versus apheresis.
In whole blood donation, you get a tiny amount of platelets. You have to pool 4 to 6 donors together just to make 1 dose for a patient.
That sounds risky. You are exposing the patient to 6 different donors at once.
It increases the viral risk and the bacterial risk. That's why we prefer apheresis. You hook 1 donor up to a machine that spins their blood, takes just the platelets, and gives the rest back. 1 donor can give a full therapeutic dose. It significantly reduces the patient's exposure.
Finally, the plasma products. FFP, fresh frozen plasma.
The key word is fresh. You have to freeze it within 8 hours of collection. If you do that, it preserves all the coagulation factors, including the unstable ones like factor VIII. It lasts a year in the freezer.
And if you thaw FFP slowly in the cold, you get this slush called cryoprecipitate.
The cryo, it is the white precipitate that forms when plasma gets cold. It looks like sludge, but it is a gold mine. It is incredibly concentrated in fibrinogen and factor VIII.
So if you have a bleeder or someone with hemophilia A, this is the rocket fuel to stop the bleeding.
Exactly. It's a concentrated glue for the clotting system.
Okay, we have the product manufactured. Now we have to match it. Section 4, the genetic code ABO and RH. This is what most people know. I'm A positive, I'm O negative, but the deeper you dig, the weirder it gets.
It is incredibly complex. It starts with Landsteiner's rules, the ABO system. The most important concept here is the difference between genotype and phenotype.
Genotype is the DNA instructions. Phenotype is the house that gets built from those instructions.
Right. If your phenotype is type A, your genotype could be AA, so pure A, or it could be AO, a hybrid. Since O is a silent gene, it doesn't produce an antigen, the A dominates. Both AA and AO look like type A in the test tube.
And the frequencies vary by race, which is important for finding matches. O is the most common.
Yes, about 45% in whites, 49% in blacks. AB is the rarest, around 4%. If you are AB, you are special.
The Landsteiner law that blows people's minds is the reciprocal antibodies. If I am type A, I have A antigens on my cells, but I also naturally have anti-B antibodies in my plasma.
This is unique to the ABO system. Most antibodies you only develop after you're exposed to something. But ADO antibodies appear naturally in babies around 4 to 6 months old.
Why? Did the baby get a blood transfusion?
No. The prevailing theory is environmental mimicry. Bacteria in your gut and pollen in the air have sugars on their surface that look exactly like A and B antigens. If you are type A, your body sees the B-like bacteria and builds antibodies against them. So you are naturally armed against type B blood.
That is wild. Our gut bacteria train our blood compatibility, and this creates the flip-flop between universal donor and universal recipient.
Correct. For red blood cells, O is the universal donor. It has no antigens. It's a stealth fighter. The recipient's immune system can't see it.
But for plasma.
The rules flip. Type O plasma is full of anti-A and anti-B antibodies. If you give that to a type A person, those antibodies will attack the patient. So type AB is the universal plasma donor because an AB person has no antibodies in their plasma.
So O for cells, AB for plasma. Got it.
Now let's talk about the RH system, the positive or negative.
We simplify to D. If you have a D antigen, you are Rh positive. If you don't, you are Rh negative. But in reality, the Rh system is a massive complex involving dozens of antigens. The main 5 are D, C, little c, E, and little e.
And the nomenclature is a headache. We have 2 warring schools of thought, Fisher-Race versus Wiener.
This was a huge scientific debate in the mid-20th century. Fisher and Race believed that the Rh system was controlled by 3 closely linked genes, D, C, and E. So they named the antigen simply DCECE. It makes sense. It's logical.
But Wiener disagreed. Wiener believed it was one giant gene complex that produced an agglutinogen mosaic. He developed this shorthand language involving R's and primes. R0, R1, R prime, R double prime.
It sounds like hieroglyphics.
It is, but if you work in a lab, you have to be bilingual. You have to know that R1R in Wiener language translates to DCE/DCE in Fisher-Race language. It's a rite of passage for blood bankers.
Let's talk about weak D. This sounds like a failed grade, but it's a genetic variant.
It causes so much confusion. Some people have the D antigen, but it is expressed very weakly. Maybe the protein is hidden inside the cell membrane, or they just have fewer copies of it.
So if you do the standard immediate spin test, they look negative.
Correct. You mix their cells with anti-D, spin it, and nothing. No clump. You'd think they're Rh negative. But you take that tube, incubate it at body temperature for 15 minutes, and add AHG, or anti-human globulin, suddenly it turns positive.
So are they a positive or negative?
It depends on the context. This is the safety first rule. If a donor is weak D, we label them Rh positive. Because if we label them negative and give their blood to a true Rh negative patient, that weak D is still enough to trigger an immune response. We have to assume they are dangerous to that patient.
But if a patient is weak D,
we treat them as Rh negative. We don't want to risk giving them a strong Rh positive unit that might overwhelm their system. We err on the side of caution for everyone.
that is smart. Now let's talk about typing discrepancies, the puzzle. This is when the forward type, the cells, doesn't match the reverse type, the serum.
This is where the detective work starts. The machine flags an error, and the human has to step in. A common cause is rouleau.
The coin stacking effect.
Yes. If a patient has very high protein levels, like in multiple myeloma or Waldenstrom's macroglobulinemia, the red cells stick together flat against each other, like a stack of coins. Under the microscope, it looks like a clot. It looks like a positive reaction.
But it's fake.
It's a false positive. You have to do a saline replacement, spin the tube, suck off the patient's sticky plasma, and replace it with clean saline. If the clumps disperse, it was just rouleau. If they stay clumped, it's a real antibody.
And then there's acquired B. This one is creepy.
It is. It happens in type A patients who have a severe GI infection or colon cancer.
What's the mechanism?
Certain bacteria, like E. coli, produce enzymes that chemically modify the antigens on the red blood cells. They strip off a specific sugar molecule from the A antigen. When that sugar is gone, the remaining structure looks chemically identical to the B antigen.
So a type A person suddenly tests as type AB.
Temporarily, yes. Their reverse type says, I'm A, but their forward type says, I'm AB. The tech has to look at the patient's history. Do they have a bowel obstruction? If yes, you suspect acquired B. You don't give them B blood, you give them A or O.
Amazing. Okay, Section 5, immunohematology. The battlefield of antibodies. We talked about ABO, but there are hundreds of other blood groups.
And this is where the difference between IgM and IgG becomes crucial. This is structural biology.
IgM is the first responder.
It is a massive molecule. It's a pentamer, think of 5 Y-shaped antibodies tied together at the tail. It looks like a snowflake. Because it is so big, it can easily reach between red blood cells and bridge the gap. That causes immediate visible clumping at room temperature.
But because it's so big,
They cannot cross the placenta. It's too large to get through the barrier. So IgM antibodies generally don't hurt the fetus.
contrast that with IgG.
The secondary response. IgG is a monomer, just one little Y shape. It is tiny. It reacts best at body temperature 37 degrees. Because it is small, it can cross the placenta.
And that makes it dangerous for pregnancy.
Extremely. If a mother has an IgG antibody like anti-D or anti-K, it can cross over and attack the baby's blood cells, causing hemolytic disease of the fetus and newborn, or HDFN.
Let's run through the other blood groups with the mnemonics from the notes. These are great. First, the KEL system. KEL kills.
KEL is very immunogenic. After the D antigen, the K antigen is the most likely to cause an antibody. If you give a K-negative patient a unit of K-positive blood, there is a 10% chance they will make an antibody. That is huge. An anti-K is an IgG antibody that destroys red cell precursors in the bone marrow. It causes severe anemia.
Then Duffy. Duffy don't bring malaria. This connects back to our deferral list.
This is a beautiful example of evolution. The Duffy antigens, Phi and Phoebe, are actually receptors on the surface of the red cell. The malaria parasite Plasmodium vivax uses that receptor as a doorway to enter the cell.
So if you don't have the receptor,
The parasite can't get in. You are immune. In West Africa, where malaria is endemic, almost the entire population is Duffy negatives, or Phi A minus B minus.
Yeah.
Evolution selected for people who lacks the antigen because they survive the malaria.
so if a patient has anti-Phi, it's not just an annoyance, it's an evolutionary marker. And finally, the KID system. Kids hide.
This is the scariest one for a blood banker. The KID antibodies, JK and JKB, are notorious.
Where do they hide?
When you get exposed to the KID antigen, you make an antibody. But over time, the level of that antibody, the titer, drops rapidly. It drops so low that our tests cannot detect it.
So the screen comes up negative.
Right. You think the patient is safe.
Yeah.
You give them Jadika-positive blood, but the immune system has a memory cell lying in wait. As soon as it sees that blood, it wakes up. It's called an anamnestic response.
It explodes.
Within days, the antibody levels spike massively and they destroy the transfused blood. This causes a delayed transfusion reaction. The patient gets jaundiced, their hemoglobin drops, and they might go into kidney failure a week after the transfusion. It's a sniper attack.
Squeaky. Now, to get these reactions to happen in a test tube so we can see them, we need help. We need to overcome the zeta potential.
Physics time. Red blood cells naturally have a negative charge cloud around them, largely due to sialic acid on the membrane. Like magnets with the same polarity, they repel each other. They keep their distance.
So the tiny IgG antibodies can't reach across the gap.
Exactly. The gap is too wide. So we use potentiators.
Right.
We add chemicals like LiSS, which is low ionic strength solution, or PEG, polyethylene glycol.
How do they work?
PEG is a water excluder. It pushes water molecules away, forcing the cells closer together. It creates a crowded elevator environment so the antibodies can find their targets.
And we have to watch out for dosage. This implies that the amount of antigen matters.
It does. We have homozygous cells and heterozygous cells.
Double dose versus single dose.
Right. Think of the M&S system. If a person inherits the M gene from mom and the M gene from dad, so they are MM, they have a double dose of M antigen on their cells. It's crowded with M.
But if they inherit M from mom and N from dad, making them MN.
They have a single dose of M. An antibody might react strongly to the MM cell, maybe a 4+ reaction, but barely react to the MN cell. It could be a 1+ or even negative. If your screening cells are all single dose, you might miss a weak antibody. That is the danger of dosage.
Which brings us to the climax. Section 6, the detective work. Testing and compatibility. The tool that makes the invisible visible is the Coombs test.
The antiglobulin test. We've established that IgG antibodies are too small to bridge the gap and cause visible clumps. So Dr. Coombs invented a way to visualize them. He created an antibody against human antibodies, anti-human globulin, or AHG.
It's a bridge builder.
Yes. If I have an IgG antibody attached to a red cell, the Ag molecule grabs onto the tail of that antibody and connects it to the tail of another antibody on a neighbor cell. It builds a chain. That chain pulls the cells together into a clump we can see.
And we have the DA and the IAT.
The DAT, or direct antiglobulin test, asks, are there antibodies already attached to these cells inside the patient's body? You use this if you suspect a transfusion reaction or autoimmune hemolytic anemia. You take the patient's cells and add AHG directly.
And the IAT, the indirect.
The IAT asks, are there antibodies floating freely in the patient's serum? This is your antibody screen. You mix patient serum with test cells, incubate them to let any antibodies attach, wash them, and then add AHG.
So let's role play. I'm the tech. I run the screen on a patient. It comes up positive. Now I have to identify the enemy. I grab the antibody identification panel.
This is a logic grid. It looks like a Sudoku puzzle. You have a panel of 11 different donor cells. You know exactly what antigens are on each cell. Cell 1 is D positive, C negative, little c positive, E negative, K positive. Cell 2 is different.
And I mix the patient's serum with all 11 cells.
Right. Let's say cells 1, 4, and 7 react. Cells 2, 3, 5, 6 are negative. Now use the rule-out method.
How does that work?
You look at the negative cells first. Cell 2 didn't react. That means whatever antibody the patient has, it's not attacking anything on cell 2. So if cell 2 has the big E antigen, you can cross big E off your list. The patient doesn't have anti-U.
You do that for all the negative cells. You eliminate the innocent suspects.
Exactly. Eventually, you are left with 1 or 2 suspects. Maybe little c is the only one not crossed out.
And to confirm it, you use the rule of 3.
Statistics. To be 95% confident, you need 3 cells that are antigen positive to react and 3 cells that are antigen negative to not react. If your pattern fits that, you can sign it out. Patient has anti-C.
And finally, the cross-match. The final hurdle before the nurse hangs the bag.
If the patient has no antibodies, we can do an immediate spin cross-match just to verify ABO compatibility. Or even a computer cross-match if the IT system is validated and everything lines up.
But if they have that anti-C we just found?
You must do a full AHG cross-match. You go to the fridge, you find a unit that is labeled C negative. You cut a segment off the tubing, you mix those specific donor cells with the patient's serum, you incubate at 37 degrees, you wash, you add AHG.
You're simulating the transfusion in a test tube.
Exactly. If it clumps, it's incompatible. Do not issue. If it's smooth, it's safe.
What if everything is incompatible? What if the patient has a warm autoantibody that attacks everything, including their own cells?
That is the nightmare scenario. You test 10 units, all incompatible. The patient is dying. You consult with the medical director. Sometimes you have to issue least incompatible blood.
Least incompatible. That sounds like a gamble.
It is a calculated risk. You are saying this blood will probably be destroyed by the patient's immune system, but hopefully it will last long enough to keep oxygen going to the brain while we try to suppress the immune system with drugs. It is the Hail Mary of the blood bank.
It really puts into perspective how fragile this whole system is. We have gone from the donor's arm through the lesion of storage chemistry, decoded the Rh genetics, and fought through the battlefield of antibodies.
It really highlights that blood banking is not just logistics. It is molecular matching. It is ensuring that a life-saving gift doesn't turn into a weapon. Every tube, every wash step, every temperature check is there to prevent the body's defenses from rejecting the help it needs.
And I'm still thinking about Kids Hide. The idea that your immune system has a memory that it can lie in wait for years, decades even, and then ambush a transfusion, it's terrifyingly impressive.
It is. It reminds us that the body never truly forgets a foreign invader. The immune system is the ultimate historian.
Something to mull over next time you see a blood drive bus.
Go.
Thank you for listening to this deep dive. Stay curious, and we will catch you on the next one.